It is time for the great L'Hôpital's rule, not the hospital. It looks like La Hospital. L'Hôpital was French. Okay, so what in fact is it? This is a BC only topic, but useful really to AB also. So basically says the following. If you take the limit as x approaches some number, could also be infinity, doesn't matter. X could approach anything of f over g, two functions, and you get, okay, plus or minus infinity over plus or minus infinity, or 0 over 0, okay? These are indeterminate forms, and not that the zeros and infinities aren't mixing and matching, but if that is the case, then what L'Hôpital's rule tells you is that this is the same as taking the derivatives of the numerator and the denominator. Don't need that underline there. Okay, just limit x approaches a of f prime over g prime. Beautiful, powerful, not the quotient rule, okay? The quotient rule would be like taking the whole derivative, numerator and denominator. And we had a famous example of this. It is the classic, so if we consider what's the limit as x approaches 0 of sine x over x. Okay, this is indeterminate because if you plug it in, it's 0 over 0. That's one of our indeterminate forms, but it's also the L'Hôpital form. So L'Hôpital's rule says, let us just take the derivative, not of the quotient, but of the sine of x, that's cosine of x, and of x, which is 1, and now it's easy, you can plug in 0, you get 1 over 1, which is 1. So that is L'Hôpital's rule in action. Okay, let's take a look at another example of L'Hôpital's rule. Consider the following. What if we have the limit as x approaches infinity of e to the x over x squared? Now, you could analyze this one and say, okay, well look, as x goes to infinity, the exponential goes to infinity greater, and so that one should win out. You know, you get infinity over infinity, which is indeterminate, but, you know, looks like the exponential should win out. Well, you can use L'Hôpital's rule to actually verify this. So we just take the derivative, right, because it's infinity over infinity, derivative of e to the x is just e to the x. Now I get 2 to the x in the denominator. Still infinity over infinity. If you plug in, do it again. So you can apply L'Hôpital's rule as many times as necessary. You get e to the x over 2. Now you can just plug in infinity, and we get infinity. Okay, so cool example of L'Hôpital's rule. Let's take a look at another one. So this one maybe is a little more interesting. So consider the following. Consider the limit as x approaches 0 from the right, okay, of x ln x. Because like h of x, it should be ln x. Okay, sometimes I draw my ln's together. Let's make it a little more clear. All right, ln x. So what's the issue with this one? Well, you have to recall, what x goes to 0, but what about ln x? What is ln x doing? And so one way I like to do it is that, okay, if you reflect e to the x, the exponential, across the line y equals x, you get the natural log of x. And what you can see there as x approaches 0 to the right, it's actually an asymptote. It goes to basically negative infinity, so you get 0 times negative infinity, which is an indeterminate form. Now, how can L'Hôpital's rule help us here? Because L'Hôpital's rule says it's in rational form, one function over another. There's a little bit of a trick, and here it goes. So x is the same as 1 over x. So if we write it like that, 1 over x, right? So x in the numerator is the same as 1 over x in the denominator. Now we've got an infinity over an infinity form, and it doesn't matter, like they don't have to be plus, they both have to be minus. Okay, it just has to be infinity over infinity. So now L'Hopital's rule applies, and we can use it. So let's use it. So we keep our limit. X approaches 0 from the right. Derivative of ln x, that's our new numerator, is 1 over x. And our denominator now is going to be negative, it's x to the negative first, so it's negative 1 over x squared. And what does this combine to give us? It combines to give us, okay, if you multiply by negative x squared times negative x squared, denominators cancel, and you're just left with a negative x. So you get the limit as x approaches 0 from the right of negative x, and that clearly now is 0. Okay, so this limit is actually 0. Now, let us do another example. Okay, so this is going to be, I think interesting. Okay, so we've got example. What's the limit as x approaches 0 from the right of x to the x power? Okay, fun one, because why? 0 to any power is 0, right? Like 0 to the third is 0. But anything to the 0 power, like 3 to the 0, is 1. So it's not obvious what this is. So let me introduce another trick. If you're ever stuck and you have an exponential, try taking the natural log of both sides. Okay, we don't even have another side here, but we can make one. How do we do that? You just try it. You say y equals x to the x. Okay, so now we take the natural log of both sides. Natural log of y equals, now if you take ln of the right side, the whole point of that is that the exponent, the x here, comes down front. And so it's x ln x. Okay, so it almost seems like we're you know, I don't know, like are we really making progress here? Well, let's find out. Okay, so basically what we have here, we know the limit as x approaches 0 from the right of x ln x. Okay, and that's what we're looking for. Well, we're looking for x approaches 0 from the right of x to the x. So this is actually good. Okay, so this is the same as the limit as x approaches 0 from the right of y, right? Because y is x to the x. Okay, that's kind of interesting. And so what can we do now? Okay, you can rewrite y as the following. You can rewrite it as, we'll keep the limit x approaches 0 from the right of e to the natural log of y. So, because the e and the ln would in fact cancel out there. Okay, now, what's interesting about this is that ln y is x ln x, right? That's what we have here. So in effect, okay, what we're doing, we have this chain here. We want to find the limit as x approaches 0 from the right of x to the x. We set y equal to x to the x. So that is the same as this. But now we do this little rewrite y as e to the ln y. And I'll write it up here. We know that this is the same as limit x approaches 0 from the right of e to the x ln x. But the x ln x piece, which is the only limit piece, we already found here using L'Hopital's rule to be 0. So this equals e to the 0, which equals 1. So that one's a little tricky, but again, I think fun. And L'Hopital's rule is awesome. Do note, it must be infinity over 0 or 0 over 0. It can't be like just anything over anything. And so you always have to make sure you check the conditions of L'Hopital's rule apply before you actually use it. As long as the conditions apply, you can use it. And you can also see in these examples, sometimes you have to be a little creative. Where, hey, even if you have like x squared here, you can make it 1 over 1 over x squared and put it in the denominator. In this particular case, if you have an exponent hanging out there, try setting y equal, taking the natural log. Sometimes you just have to try some things. But it's a great tool. It'll definitely make your life easier, and it can be used to solve a lot of indeterminate forms, kind of like this one where you have 0 to the 0 power. Note that it is 1, and the power, the x, wins out.